All right, everybody, welcome once again to the CUNY set theory seminar, which is still going strong and virtual. And today we are very happy to once again have Andrew Brooke-Taylor from the University of Leeds. And maybe next time we'll have him in person. Who knows? This is all very hopeful. And Andrew is going to speak today on categorifying Borel reducibility. Go ahead, Andrew.
Thank you. So thank you all for coming, and thank you for the invitation to speak here. What I want to talk about today is the project that I was meant to be coming to the US this semester to work on with my collaborator, Filippo Calderoni. But as you heard from the previous chat, that hasn't happened yet, but hopefully soon. So yes, categorifying Borel reducibility. So I want to start by talking about, I want to start by talking about Borel reducibility and what it's been really useful for. And this is, I want to talk about broad brushstrokes look at classification problems. So when we talk about a classification, in broad brushstrokes, this should be something that takes mathematical objects that we want to classify, and this will possibly be up to isomorphism or some other equivalence relation, and we want to map them by some reasonably definable map to some other intuitively simpler objects, the invariants that we want to use to classify our mathematical objects. And again, the variants are possibly up to isomorphism or some other equivalence relation. And obviously this classification, it should respect these equivalence relations. It should also respect the non-equivalence. If you have different objects, then the whole point of the classification is that they go to different invariants. So now, often these objects that we want to classify and also the invariants that we want to use to classify them, they can be encoded by reals, or if you want to be a bit more general, members of a complete metric space with a countable dense set. So that's what's called a Polish space. Or even if we just forget the topology and just remember which sets are Borel sets, what's called a standard Borel space. So a classification should take a standard Borel space with an equivalence relation by some reasonably definable map to another standard Borel space with an equivalence relation, respecting the equivalence relation and its negation. So then what should reasonably definable mean? Well, in this setting, Borel, so the inverse image of any Borel set is Borel, that's a suitably liberal interpretation of reasonably definable. So that's the very broad framework of Borel reducibility. And so here's the definition. If you've got X and Y standard Borel spaces, E an equivalence relation on X, F an equivalence relation on Y, we say E is Borel reducible to F if there's a Borel function from X to Y such that two elements are E equivalent if and only if their images are F equivalent. Now, the point as I was motivating with this classification blurb was that if you can show that there's no such Borel reduction, then that tells you that if you had some grand classification program involving these objects and these invariants, but you've proven there's no such Borel map, well, that proves that the classification program cannot be sort of fully executed, cannot be completed. And so this has been used to great effect, giving important unclassifiability results in ergodic theory, C-star algebras. So it's a really useful tool. So before I go any further, I want to give a really important example of this. And that is with first order structures and first order logic. So if you've got some countable vocabulary or language, if you like, with relation symbols and function symbols, well then, if you've got a V structure with underlying set the natural numbers, you can encode that by a single characteristic function in this product space, where for each relation symbol Rm of arity Am, well, think of the characteristic function of the relation. For each Am tuple of natural numbers, you say yes or no whether it's in the relation. So Rm is encoded by this Rm component of 2 to the n to the Am. And similarly for the functions, if you've got Bn tuples from the naturals to the naturals, well, that is just a function. And so this is basically copies of the Cantor space product with copies of the Baire space. And so in particular, these are your very standard examples of Polish spaces. So with that view, if we call this structures for V, then we have this space, well, we have this nice Polish space of structures. Now notice in particular, I've assumed the underlying set is always the naturals. This is always about countable structures, but as soon as you're countable, well, you might as well assume that the underlying set is the naturals. So there's no harm in going concrete in that way. So once you've got all V structures, well, then you can consider some first order sentence phi, and you can consider the subspace of all models of phi. Okay. And then we consider the isomorphism equivalence relation on those structures. And so this is a nice class of mathematical objects, these structures for V, or these models for phi, up to isomorphism. And so being a key example, it's interesting to ask, well, if you consider all possible algebraic sorts of structures like this, classes of structures like this, well, then you can ask, is the isomorphism relation maximal in this Borel reducibility sense? So Friedman and Stanley, in their original paper introducing Borel reducibility, they defined the isomorphism relation of a class of structures like this to be Borel complete if every isomorphism relation for a class of structures like this Borel reduces to your isomorphism relation for phi models. Okay, so Borel completeness is kind of the key notion within within Borel reducibility that I want to sort of keep coming back to in this talk, but it's really just an example for the generality, the generalization of the framework that I want to give, but it's an important one. So Friedman and Stanley, and subsequently other people, have shown that all sorts of familiar classes of objects are actually Borel complete with the usual notion of isomorphism. So graphs, groups, rooted trees, linear orders, fields, Boolean algebras, even quandles, if you know any knot theory. So these are all Borel complete classes. All right, so that's kind of a quick introduction to the basic Borel reducibility framework. Now, the title was Categorifying Borel reducibility. Let's touch on category theory. I'm sure you've all seen some definition of category theory before. there are different ways to present it. I want to view it this way, where we have a class of objects and a class of morphisms, and that's a category. And then you can view the extra structure of the category as being given by functions between these classes. So the domain and codomain, they're functions from the class of morphisms to the class of objects. For each object, you have an identity morphism. So you've got an identity morphism function. And then you've got a partial function. Composition is a partial binary function from pairs of morphisms to morphisms. And these should satisfy all of the usual category axioms. You've got associativity of composition, and the identity behaves the way you want it to. Okay, so in particular, the example I gave before for first order structures, we have the category whose objects are all models for some formula and whose morphisms are the V homomorphisms. And so such a category is called an algebraic category. And then a functor is basically a homomorphism of categories. It takes objects to objects, it takes morphisms to morphisms in a way that respects composition, identities, domains, codomains. So with that quick category theory background set up, let's look again at classification. The point is that often a classification should not just take objects to objects, or rather, I guess, take objects to invariants in a nice definable way, but in a lot of areas, the kind of mathematicians working in that area want these classification maps to be functorial, what's more. So for example, we mentioned C-star algebras earlier. You've got these K-theory invariants that are used in C-star algebras, and these are functorial invariants, okay? They respect not just the objects, but also the morphisms. But the Borel reducibility framework just pays no heed to the morphisms at all. And so the idea here is to extend the Borel reducibility framework to accommodate this, and then have a look at how this changes things. And actually, we see that quite a lot of classes of structures that were Borel complete, we can actually fairly readily show that they're not universal in the analogous way for this extended Borel reducibility framework with functoriality. So, okay, let's give a definition. So a Borel category, taking the place of the standard Borel space of objects, standard Borel space of invariants, we're going to have a Borel category of objects and a Borel category of invariants. So a Borel category is just a pair of standard Borel spaces where you have a space of objects and a space of morphisms. And then in the way I set up the category theory definition with the functions between those classes, it's just all the same for that in such a way that these objects and morphisms with those functions form a category. So let's go back to our standard example. Well, morphisms between structures on the naturals, you might just think of, oh, that's n to the n, the bare space. But we want to be a little more refined than that. Given a morphism, given a function from n to n, we want to also declare which structure we are thinking of it as coming from and going to. So my space of morphisms is actually going to be a subset of this triple Cartesian product of two twice the category of structures, twice the space of structures, and then the bare space, the functions from n to n, consisting of those m, n, and f, such that f is a homomorphism from m to n. Okay, and then with that notion of what a morphism is, then you get very naturally a Borel category. And it's very straightforward to check that the identity maps, domain, codomain, all these things are nice and Borel. And then, well, that was for all V structures. And so then again, if you've got any first order sentence, you can look at the Borel category of models for that formula, where you just take the models and just like in any first order setting, the homomorphisms for the models is just all the homomorphisms between those things as structures. So that gives us the Borel category. So that's kind of the overarching example. Most of my examples are going to be of this form, but it is a more general framework. It can accommodate much more general sorts of Borel categories. So hopefully, the idea is that hopefully this will be a widely applicable framework. But as I said at the start, this is still work in progress. Anyway, it may be work in progress, but we can already say some things. But first of all, a Borel functor is what you might expect it to be. It should be a functor from a Borel category C to a Borel category D in a Borel way. So what does that mean? We just want that the functions, the object function and the morphism function, they should be Borel functions. And then it should be a functor. So they should respect domain, codomain, identity, composition. Now, the first thing to note is that Borel functors must respect isomorphisms. So if you've got the category theoretic definition of an isomorphism, that's just an F such that there's a G, such that G of F is the identity and F of G is the identity. Well, then from the fact that you respect identities and composition, we get that a Borel functor must take isomorphisms to isomorphisms. But they don't need to respect non-isomorphism. So we need to have a stronger notion than just having a functor there in order to expand on the isomorphism equivalence relation framework of standard Borel reducibility. So some special kinds of functors. These are very standard category theoretic definitions. A functor will say it's full if for any two objects, then F restricted to the morphisms between those objects is surjective. So if you've got a morphism G from F of C0 to F of C1, well, then that G is the image of some little f. So full is basically surjective on morphisms. Faithful is injective on morphisms. Okay. Mm-hmm. And then we have this standard kind of jokey terminology. A functor is fully faithful if it is both full and faithful. And then one step further, we say that a functor is a full embedding if it's full and injective, not just on the morphisms, but also on the objects as well. Okay, so the point here is that a fully faithful functor, it can fail to be an embedding by identifying isomorphic objects to each other. So from a standard category theory perspective, yeah, isomorphic objects, they might as well be the same thing. It's fair enough to blur the distinction there. But when we're talking about Borel considerations, situations where you may not have a Borel selector, for example, then it's important to maintain this distinction. Okay, so we're going to define a functorial reduction from a Borel category C to a Borel category D is just a fully faithful Borel functor from C to D. Okay, the most natural thing you could have for this framework. And then the proposition is that the object map of a functorial reduction is a Borel reduction of the isomorphism relation on the objects for C to the isomorphism relation of the objects from D. Okay. Now we already showed that any functor respects isomorphism, so we need the converse direction. We need to show that, to prove this, we need to show that if you have f of C0 and f of C1 and you have an isomorphism between them, then there was an isomorphism back on the curly C side. Okay, and for this we use fullness and faithfulness. So if you've got such an isomorphism, so what does that mean? You've got morphisms H one way, J back again that compose to give the identity. By fullness, those H and J are images of something under F. And then by functoriality, if you look at F on the composites of the things that gave you H and J, well, that gives you F of the identity. And so by faithfulness, since the identity is the unique thing going to F of the identity, we have that the composites of these things on the C side are both the identity, and so they're isomorphisms. Okay. So simple chasing backward and forwards category theory style argument, showing that a fully faithful Borel functor gives you a Borel reduction of isomorphism. So this is going to be our notion of a functorial Borel reduction. Okay, so going back to the classification perspective, one issue you might have with this is, okay, even if you accept that in some areas of mathematics you should classify things with functors, well, it would be reasonable to allow multiple different functors to distinguish different objects. But this is fine. If you've got any product of a countable collection of Borel categories, it's going to be a Borel category. And if you've got a countable collection of Borel functors, then the product functor is a Borel functor. So you can incorporate all these countably many invariant map functors into a single one. And so we don't lose any strength from the idea of a classification if we talk about just a single functor.
Can I ask a question?
Sure, go for it.
So I see that countably many Borel functors become one, but if the countably many given functors are full, does it follow that the one is full? Because it seemed that the components in different Ds of a single morphism in the product could need to be lifted to different morphisms in C.
That's a very good point. Yeah, no, you're right. So I guess this doesn't make the point that I was hoping. Yeah, I guess you want not just C there, but the countable product of copies of C. That would hold water, but then that's not exactly what we want. So that's a good point. Yes, I hadn't thought of that. Thank you. I have to work on my patter for why this is fine. So, but in any case, for this talk, that's all I'll be looking at, is a single functor. Okay. So now this is a proposed framework. So then the questions are, how does this compare with ordinary Borel reducibility? So there are some arguments in the literature that are very naturally functorial, but many of them are not. And then also there's a pre-existing category theory literature of a very similar flavor. And so then the question is, how does this compare with that category theory literature? And actually, we've found in our work so far that it's being most fruitful to mine the category theory literature rather than the Borel reducibility literature, because it more often carries across. Because frequently these constructions from the category theory literature are hands-on. And there's this kind of, if you've worked with Borel reducibility at all, or descriptive set theory in general, there's this kind of Church's thesis for Borel, which says any definition you make in a reasonably hands-on way, it's going to be Borel. So because these are hands-on definitions that the category theorists in the 60s were writing down, well, they do in general give you a Borel mapping. But we do need some care because we want to keep the constructions countable. We want to go from countable structures to countable structures. And that's something that hasn't in general been a consideration in the analogous category theory literature that's out there. So a lot of this is kind of cheap theorems by looking at the right place in the analogous literature, but you always need to be careful and some bits do need tweaking. Okay, so then our notion that I particularly pulled out early on of Borel completeness, if we categorify that, we can say a Borel category of this form models for some formula, let's call it functorially universal if every Borel category functorially reduces to it. We weren't quite sure what to call this, but so yeah, if you've got a better suggestion than functorially universal, by all means, let me know afterwards. But this will do for today. So then the question is, okay, we've got this whole literature from the Borel reducibility world of these Borel complete classes of structures. Which of them, when you go to the functorial setting, which of them become functorially universal Borel categories? Some do and some don't. So the granddaddy of them all is the category of graphs. And so set up notation, I'm going to use GRA to be the Borel category of directed graphs as ever on underlying the natural numbers. And then with directed graph homomorphisms as the morphisms. So this is just the category of structures for a single binary relation. And so basically in any setting you make up, graphs is going to be the universal thing. And the same is true here. Graphs is functorially universal. So as I said, in different similar kinds of frameworks around the literature, there are sort of different proofs appropriate to it. But when we were looking at this, none of the proofs that we found really carried across just immediately. So in the model theory setting, you've got this context of interpretability, and there's an analogous proof in Hodges. And that gives you something, it's even functorial, but it's not actually full. And then in the category theory literature, there's a proof, but that one has the problem that I raised earlier, that it doesn't preserve countability of the structures. But we can tweak things to make it work. So I want to talk through this to kind of give a flavor of the kinds of constructions that we do in this area. So following this category theory literature, a key step, the one that kind of doesn't immediately translate across, is to show that for any countable relational vocabulary, there's a countable binary relational vocabulary such that structures for V functorially reduces to structures for W. And in fact, the proof shows that there's Borel full embedding. So we do these kind of constructions, we show there are these embeddings with hands-on constructions. Given a V structure, we want to create a W structure that basically encodes all the information of the V structure. So not only can you get back the V structure from the W structure, but also it's sort of rough that the only morphisms between the W structures are the ones that came in the natural way from the V structures. So that's how we prove this. We basically build on the construction in Poulter and Turnkover's book, but in their construction, their structure, the W structure N that they build has this underlying set with tuples from the naturals where they just give once and for all, they say, okay, take the supremum of the tuple lengths and then take that length tuples from the naturals. So that's awkward if you've got literally a countable, countably infinite vocabulary with unboundedly large relation arity, okay? But hopefully it's immediately plausible that with just a bit more care, we're gonna add in one extra binary relation to keep track of the tuple length, then we can build an encoding structure in the same way. So let me give you some details, but it's mostly going to be pictorial. So let's say I've got these V relations, Ri of arity Ai, and I'm going to take a binary relation with a symbol, a binary relation symbol Ri for each of the Ri's that we originally had, so Ri bar. I'm going to have things I call Sn, and then we've added a final binary relation T. And then I want to define from a V structure M, a W structure N, defining Ri, Sn, and T in this way. Don't bother reading that. Here's the picture, at least for T, okay? This binary relation T is on arbitrary tuples, but it's only ever mapping between constant tuples, okay? And it has this structure that each n tuple is in relation to the n+1 tuple of the same element. And then we've got the extra relation that the empty tuple is in relation to all the pairs, constant pairs. So why do I have that in? The point of that is that this is part of what gives us the rigidity such that any W structure, any homomorphism of W structures must come from a homomorphism of the V structures we started with. Because what happens if we have a homomorphism of W structures with a T relation like this? Well, any of these columns in the T relation for a given entry in the increasing size tuples, well, because of the sort of triangle at the bottom of the column, if you look at the image of that under your W homomorphism, then that must also go to a triple of elements of your image W structure that also has a triangle of T relation. So that tells you that any of these triangles must map to another one of these triangles. And then once you've got the triangle, then going up from there, say 0, 0 is in T relation to 0, 0, 0. So whatever 0, 0 goes to, 0, 0, 0 must go to whatever you get from that relation. And so from this T, that tells you that whatever your W homomorphism is, it acts on constant tuples by a single function. Your W homomorphism G on an n tuple of x's is just an n tuple of y's for some y depending only on x. Okay, so I hope this isn't too hand wavy, but this is the point. These extra structures, these extra relations give you this rigidity that any W structure homomorphism, you can say, well, it must respect tuple length. And then the S relations are just saying, oh, if you've got two tuples of the same size and the second tuple is actually the constant tuple given by the nth entry of the first tuple. So that will then say, oh, whatever this W homomorphism is, it acts component-wise on all the tuples. Okay? And so once it works component-wise, well, then it must have come from a function between the V structures. And then you've got these R relations that tell you that the only homomorphisms came from homomorphisms. Okay, so that gives us this proposition that you can code arbitrary relational structures into binary relational structures. And then once you've got binary relational structures, you can encode binary relational structures into just single binary relational structures, i.e. graphs, and that fills out the proof. But that much is actually, you can just lift it from the category theory literature. There are no worries with that. So in this generalized framework, graphs are indeed universal, as you would hope. Okay, so now let's start looking at some areas where it's different from the Borel reducibility sort of standard framework. And so I want to start with what's called mono-unary algebras. This is basically the first example in Friedman and Stanley's original paper. I mean, they take for granted that graphs is Borel complete, but from that point, basically the first example they give is these mono-unary algebras. They show that structures for a mono-unary algebra is a Borel complete class of objects. But it's not functorially universal. So already we're getting separation from our generalized framework, from our categorified framework to the Borel reducibility framework. And how do you show that? Actually, a lot of these non-universality arguments just come from making the right observations about the automorphism groups or the endomorphism monoid. And so it's an old result of Heyderlin and Poulter that if the endomorphism monoid of a mono-unary algebra is a group, then in fact it must be a direct product of cyclic groups. Okay, old fact there. And so once you know that, well, then that rules out functorial universality for these mono-unary algebras, because, well, how do we show that? We come up with a sum structure for some language with endomorphism monoid S3, a group that is not a product of cyclic groups. So here's an example. I've taken a binary relation, a unary relation, and set things up so that this structure for that language its endomorphism monoid is precisely S3. It's a group, but it's not a product of cyclic groups. So it cannot embed respecting the endomorphism monoid into, it cannot be encoded by a mono-unary algebra. So we do have a difference from this, from standard Borel reducibility. So actually, let me briefly say, I mean, the ideas I'm presenting here, they're not, well, so even back in the original Friedman and Stanley paper, they mention the idea of categorifying things, but they say, oh, we're not going to pursue that because, well, we don't feel like there might be many positive results. Okay. I mean, irrespective of that, I hope I've convinced you that with the kind of use of Borel reducibility for classification problems, this is worth looking into. But even so, it's kind of nice that we can go one step further and we do get something that is actually functorially universal. So if you've got two unary function symbols, then that is functorially universal. And how do you do that? Well, the idea is if you think of, we want to embed the category of graphs into the category of di-unary algebras. Well, the way to do it is now think of a graph as a set of vertices and a set of edges and create the di-unary algebra. So you've got the underlying set of the vertices along with the edges, along with two extra vertices for coding stuff up. And then you just, I've said, right, so if you've got an edge in the graph, well, so that's going to be going from some V0 to V1. Well, let's take f of E to be V0 and g of E to be V1. So by having two unary function symbols, we can sort of pull out the domain and the range for these directed graph edges. And then we extend it f and g on V and on 2 in a suitable way that you've got the same kind of rigidity that I kind of worked so hard for in the example I did before. That's actually an easier case, but you can set it up that way and in such a way that the only homomorphisms between the di-unary algebras you get this way are the ones that come from graph homomorphisms. So di-unary algebras, it embeds graphs, and so in particular, it embeds anything. Okay, there is something to think about maybe here of, okay, this change of mindset from edges being a relation on the vertex set to a set in itself. Does that work with this whole framework of having the natural numbers as your underlying set? The short answer is yes, it does work. There's something to think through there if you're not used to it, but it works. So another Borel complete category. Let's do some more kind of real mathematics, as it were, examples. So one very nice, I didn't want to be disparaging there. I just meant sort of examples that sort of might come up in other areas of mathematics more naturally. So linear orders. Friedman and Stanley showed that the isomorphism relation for countable linear orders, that's Borel complete, but it's not functorially universal. And the argument here, again, it boils down to the automorphism group. If you have a non-trivial automorphism of a linear order, then it must have infinite order in the automorphism group. So to show that linear orders is not functorially universal, it suffices to just come up with some structure with a finite automorphism group. So here's one with automorphism group Z mod 3. I could have used the same example as before with S3. All right, Boolean algebras. So Camerlo and Gao showed that Boolean algebras, its isomorphism relation is Borel complete. But again, this is not functorially universal. And again, it's about automorphism groups. A lot of these results are, you got to dig through the literature for the right automorphism group results, but once you find them, it's easy. So in this case, Mackenzie and Monk showed that every element of the center of the automorphism group of any Boolean algebra has order at most 2. So if you unpick that, you realize that a Boolean algebra cannot have automorphism group Z mod 3. So the same example as I used last time shows that Boolean algebras is not functorially universal. Okay, so hopefully you're starting to see a lot of examples aren't universal in this framework, but some are. So there are natural questions here about what still works, what doesn't. We're still kind of building up what we know about these things. Some bigger questions here is, well, these impossibility of classification results that I motivated all of this with, they generally use Hawth's notion of turbulence. So can we find a categorified version of that? That is something I would love to figure out. I'm hoping to, spend some time thinking about that. So one of the problems with that is a nice thing about isomorphism of structures with the naturals as underlying set. Well, these isomorphisms are basically, the isomorphism relation can also be viewed as the orbit equivalence relation of the S infinity action on your class of structures. Because an isomorphism between structures on the naturals is just a function, is a permutation of the naturals. And in fact, if you think about it, it goes the other way as well. Any permutation of the naturals gives you an isomorphism. So isomorphism is intimately tied up with this S infinity action on our space of structures. That's for the Borel reducibility kind of original framework setting. Everything works nicely here, nicely there, but here we've got this somehow different perspective on isomorphism. It's just there are homomorphisms each way that have nice composites and things fall out of that. Are we going to be able to generalize turbulence to that framework? So yeah, we'll see. And so then the point of that is, can we use this framework to show that some classification program out there in the mathematical world is impossible to resolve, using it for an example where standard Borel reducibility was too blunt a tool. So those are kind of the big targets that I'd like to get to one day. But I think I'll leave it there. Here are a whole lot of references for things I've been saying. So thanks.
Thanks very much, Andrew. Okay. Do we have questions?
Is somebody talking right now? Maybe it was Andreas. Hey, Andrew.
Hi, Tibor. Good to see you.
Long time no see. I'm in the Netherlands. I'm only guessing, how many miles I have from various people on this call. Look, I am a very simple-minded person, as you know, and I know nothing about Borel relations and that relation. But I'm familiar with the Prague school a little bit. And I think the point of view they took was basically about embeddings of large categories, at least in many cases. So like a typical statement of the Prague school is that, I know every accessible category has an accessible full embedding into the categories of graphs. Right. And then you take like a chunk of it, just like, the first kind of, omega presentable, omega 1 presentable part of it. And is there, you almost are saying that there is a conceptual translation from these embeddings and non-embedding theorems to the Borel category setting just by looking like the initial chunk of that construction. Because, because of accessibility, if you know what's happening up to omega 1, you kind of extend it tautologously all the way through the ordinals.
Right. I mean, I haven't been thinking about it in any such general terms. I mean, my perspective on it was always just, well, there's this wonderful body of literature, as you say, tends to be on large categories, but the constructions very frequently, as I said, are just hands-on constructions. From a V structure, you build a W structure. And these hands-on constructions, well, you can restrict to countable structures. And then as long as the image is also a countable structure, because it's hands-on at Borel, it's Borel, so it does carry across that way. I suspect it probably doesn't go so much in reverse, but I don't really have examples of that. I could imagine things where you've got a Borel embedding, but it's sort of very reliant on the fact that you're only looking at countable things, and so it's not going to pull up to the full class size category. But I don't have any examples of that as yet. Basically, I motivate this from the Borel reducibility side, but the kind of theorems that I'm pulling down from the literature, I'm pulling them down mostly from the category theory literature, not the Borel reducibility literature. So yeah, I'm also interested to see points where it differs from the existing category theory literature as well. So yeah.
Thanks a lot.
Let me ask a question about the foundations of categorification.
Sure.
So you require fully faithful functors in order to make sure that non-isomorphism is preserved.
Right.
But you don't need the full strength of full faithfulness for that. You could have a theory like this that only requires what you actually seem to need, namely that the functor creates isomorphism, so that if you have an object mapping to it, and then an isomorphism to another object, you can get the isomorphism pulled back.
Right.
To an appropriate second object. That would still get you what you need for non-isomorphism, but it would mean that you're not being quite so restrictive on what happens to morphisms other than isomorphisms. In particular, as far as I can see, your arguments for the non-universality or the non-functoriality of linear orders and Boolean algebras would still go through, because those look at the automorphism group. But when it comes to the mono-unary algebras, that one looked at the endomorphism monoid, and presumably that really used full and faithful, and not just creating isomorphisms. So I guess with that long preamble, the question is there anything that can be reasonably said about this, shall I say, more liberal notion of functorial Borel reduction?
So the short answer is I haven't thought about it. It's a great observation. That's definitely an interesting. Yeah, good question. I don't know.
I do have another comment, but maybe I should, if there are other questions, I'd let other people ask. Well, as long as everybody is not asking, I'll ask another. Actually, it's not a question, it's a comment about the sort of foundations. Why is Borel a reasonable notion to use here? And I agree with what you said about anything that people reasonably define is likely to be Borel. But there's actually a fact about, you mentioned sort of a variant of Church's thesis, which I think might be called CUNY's thesis here. And I sort of suspect that only old folks like me actually had to learn about CUNY's higher type recursion stuff. So CUNY developed recursion relative to objects of higher type. And if you look in particular at the type 1 objects are function, 0 is natural numbers, 1 is functions, natural numbers, 2 is functionals that take those functions as arguments. There's a type 2 object, which he calls prefix 2e, so pre-superscript e, but 2e is existential quantification over numbers. It takes a function as argument and produces a 0 as output if there's at least 1 0 among the values of the function and 1 otherwise. So it embodies number quantification. And then one of the things that CUNY proved about this is that if you do recursion relative to that 2e and arbitrary reals as oracles, that gives you exactly Borel. And if you disentangle what his recursion definitions really mean, it's essentially saying, if you take ordinary recursion theory and every place where you want things to be finite, the inputs, the outputs, the programs, the computations, every place where it says finite, allow countable instead. That's Borel. And I think that provides a rather firm underpinning for the sort of thing that you were saying about reasonably definable implies Borel.
Okay, that's really good to know. Thank you, Andreas.
Yeah. Yeah. Also, you had that, going back to Borel, Zara, that work has been called semi-intuitionism, right? By the set theory people.
Yeah. I conjecture that there are a lot of things that have been called semi-intuitionism, and I'm reasonably sure that you're right that this is one of them. You take intuitionism and you take half of it, but they don't tell you which half.
No, but it's just to shore up the idea that Borel is a firm category to work with.
Mm-hmm. Yeah, there's sort of,
I mean, one point to make. Go on, Andreas.
well, all I was going to say is that as far as I can see, there are 2 rather broad bodies of mathematics in which intuition of defining is formalized. In many places like here, Borel. In California, L of R.
Well, actually, this touches on the point I was about to make, is that if you look in Horst's book, classification, well, I forget the name of it, but if you look in his classification book, he makes this point that actually a lot of the theorems he's interested in, it's not crucial to them that you're using Borel and have even more liberal notions of definable, and you still get a reasonable theory out of it. So, and I think he does even mention L of R somewhere in that. So.
Any other questions, comments? All right, Andrew, then thanks once again for the great talk, and it's good to have you here, and hopefully we will see you in person sometime soon.
I hope so too. That'd be great. Good to see you all.